Of attenuation. Everybody kind of went over the attenuation coefficient? Yeah. We're good on it? Okay, I'll explain. Still. So, the attenuation coefficient is the number of decibels of attenuation that occurs when sound is traveling 1 meter.
Centimeter.
1 centimeter. I'm sorry. Okay? So, our units for attenuation are going to be decibels per centimeter. Okay? Decibels per centimeter. All right? So the advantage of the attenuation coefficient is that that value remains constant. No matter at which depth, the value that which sound loses energy is going to remain constant every centimeter. All right? It's not like it's going to lose 2 decibels at 1 centimeter. Then when it gets to 4 centimeters, it's going to lose 5 decibels. It's going to maintain the same decibel loss per centimeter. Okay? So, regardless of how far it travels. So, the example the book gives you is that sound is traveling in a specific tissue. Key word here being, guys, specific tissue. Okay? Because there is a different coefficient for soft tissue by itself. So, when it's talking about the attenuation coefficient, we're talking about basically like a generalization of all the media in the body, from air all the way to fluid. Okay? So, sound is traveling at 2 decibels per centimeter, and the sound beam travels at a depth of 8 centimeters. To find out what the attenuation coefficient is of this beam right here, then all we have to do is multiply the attenuation coefficient, which is 2 decibels per centimeter. Okay, when we're talking about a specific tissue, the attenuation coefficient is 2 decibels per centimeter times the distance traveled. Okay, times the distance traveled. So no matter what, so in this case, our attenuation coefficient in a specific tissue is 2 decibels per centimeter, traveling at a depth of 8 centimeters. Multiply those two numbers, and you're going to get your attenuation coefficient, which should be the total attenuation of 16 decibels. Okay? So even if we were traveling, 20 centimeters, what would our attenuation coefficient be? Do I need to put it on the board, guys? No. Anybody need to see it on the board? Anybody? Please speak up if you need to see it. Don't let the nose discourage you, please. 40. It's going to be 40. Exactly. It's going to be 40 decibels of total attenuation. Okay? Remember, key word here being, guys, specific tissue. If I'm talking about soft tissue, we're not going to use that same 2 decibels per centimeter. Okay? Golden?
Is there one for specific?
It is. That's why I'm specifically saying that. All right? We're good on the attenuation coefficient in a specific tissue. All right. Ooh. So, in soft tissue, though, the attenuation coefficient and the frequency are directly related. Okay? So, of course, we already know that scattering and absorption are directly related to the frequency. The higher the frequency, the more scattering, the more absorption. All right? The attenuation coefficient is 1/2 the frequency. Hopefully that's an easy one to remember. We're talking about soft tissue, okay? Specifically soft tissue, which we know that is going to travel at a speed of 1540 meters per second. A mile a second. All right? So it has two different ways of explaining the formula. It means the same thing though, okay? So attenuation coefficient is the frequency divided by 2, because the attenuation coefficient in soft tissue is 1/2 of the frequency. Okay? So if we're doing the thyroid with a 12 frequency transducer, what is my attenuation coefficient in soft tissue? 6 what?
6 decibel over centimeter over millimeter.
6 decibels per centimeter. Okay, we're using a 12 transducer. We're using a 5 transducer for an abdomen in soft tissue. Our attenuation coefficient is going to be 2.5 decibels per centimeter. Okay, because it's just 1/2 of the frequency. Okay. Key words being soft tissue. Key words being soft tissue. So you can also express that in another way. 1/2 decibel per centimeter per megahertz is another way to express that. They give you both ways, but they mean the same thing, right? Yes? Unison, yes? Okay, late in the day. Y'all don't have no energy for me. I already ate and everything. I have energy. Okay. So for each centimeter that sound travels, most energy is lost from high frequency than from low frequency sound. I probably said that already, guys, like 4 or 5 times a day. high frequency sound is gonna attenuate faster than lower frequency sound. Even if you gotta, when you're taking a test, if you just gotta think about, man, we did an admin, that's the 5 transducer, we were able to look deep. But when we did a thyroid, that was a high frequency 12 transducer, we wasn't able to penetrate deep. Even if you gotta do that, because when I was doing my test, I was up there, when I turned the color, when I took my vascular test, I was like, okay, I turned the scale down. Okay, that lady came in, what are you doing? I say, I'm imagining a machine. Even if you gotta do that, use what you gotta use, okay? Myra, it was proven, right? When we went to lab the other day and we did a thyroid, how much better. Remember, higher frequency is also gonna give us a higher quality image. Gonna make our axial resolution a lot better, okay? So we did a thyroid the other day with 3 different transducers. We started with the 12 transducer. Beautiful images. I don't want anybody to have any pathology, but I hate that we didn't have somebody with thyroid nodules because you really can see the difference. Because you have thyroid nodules, we're gonna see it really clean with the 12 transducer. Y'all seen thyroids, right? Y'all seen people have goiter and cysts and masses on their thyroid?
Everywhere.
Oh my gosh. Yeah, but that's possible, man. That is possible.
We had yesterday inmates.
Inmates?
Inmate coming for pilot, yeah.
Right. So luckily, all of you guys are super healthy. We didn't have anybody like that to do it on, but the 12 transducer showed the thyroid really great. Next transducer we used was the 5. Man, we could barely see that the thyroid even existed. Right, Myra? You don't have to take my word for it. Take Myra's. That's the Reading Rainbow guy used to say.
Is that real?
Yeah, take my word for it. Take theirs. Then the last transducer we used was the 9 megahertz transducer, which is the linear probe, right? Which kind of was like, muscle mammals, it was all right. It wasn't bad, but we weren't able to see the minute details such as in the muscle, or the very near field, okay? Which is called the dead zone. The dead zone, which is the closest area to the transducer, okay? We're good here. Attenuation coefficient in a specific tissue, Adelie? Farnaz? 2 decibels per centimeter. In soft tissue, Myra?
0.5.
Half of the frequency. Half of the frequency. So be careful when I'm asking questions, know what I'm asking for. If I say soft tissue, know that it's half the frequency. If I say in a specific tissue, then know that I'm talking about, it's about average about 2 decibels per centimeter. We're good there? Good there, guys? Sweet, sweet. Mind you, now we're just talking about ways to calculate attenuation. After we got finished with absorption, the next three things, attenuation coefficient in soft tissue, and its half value layer thickness, those are all different ways to measure attenuation. Okay? Not to be confused with absorption. All right? Right, because I know the book doesn't have a clear delineated line where it's like, boom, I'm moving on. I'm past the 3 components. All right? So, attenuation coefficient in media other than soft tissue, you guys kind of already know this. The brain, the kidney, the liver, those examples of soft tissue right there, guys, right? Okay. Air has an extremely high attenuation rate, right? Because it's going to undergo a lot of scatter and absorption, correct? So again, like I told Dewey earlier, a frequency with a frequency above 1 megahertz is going to attenuate entirely, which is why you can't see lung tissue. Because we don't, in diagnostic ultrasound, we don't deal with transducers that are 1 megahertz or below. Okay? But if we did, we may be able to see some lung tissue. Maybe. But then with a 1 megahertz transducer, what would that quality be like, right? Wouldn't that be this horrible quality? Would we be able to see any kind of lung cancer? Do you think so, Myra? Probably not, because those are not going to be high quality images. Okay? So the main mechanism of air is absorption. Okay? Similarly, the lungs attenuate dramatically. Guys, I'm just kind of going down a little chart. If you're looking at the little chart in the book on page 86, that's all I'm doing. Table 6-4. Okay? Similarly to the lungs, lungs attenuate dramatically because why? They have air, right? Because of scattering, not absorption. All right? Bone also absorbs sound to a great extent. Okay? We're going to talk about impedance in a second, and that's why you get that big bright reflection on when you're looking at bone, because the impedance difference between bone and the tissue around it is so great, and that's going to provide a higher reflection or a brighter intensity reflection. Okay. biologic fluids attenuate far less than soft tissue. Again, that's why we have, when we're looking at, oh, this is a perfect example. Think about absorption. Think about when we're looking at a gallstone. Everybody's seen a gallstone, right? Everybody's seen a gallstone. What artifacts associated with a gallstone?
Shadows.
Shadowing, right? That's why, because that sound is being absorbed, which is why we can't see anything posterior to it. That's why we don't get reflections posterior to it. Okay? When we talk about biologic fluids such as the bladder, the a good clean gallbladder is going to have that acoustic enhancement posterior to it, because fluid is not going to attenuate as much as a structure such as bone, okay, or a gallstone. All right. So water has the least amount of attenuation with no noticeable loss in energy with frequencies less than 10 megahertz. Okay. Muscle is unique in sound in that sound traveling across the muscle fibers attenuate twice as much as when sound traveling along the length of the fibers. We know what muscle fibers look like, huh, guys? Yes. If you don't know, bang, we got some muscle fibers right there for you, okay? So when you see muscle, we're talking about the striations, right? So what they're saying is, you see how the striations are going this way? This way, everybody can see how they're going the long way this way? So that means that if my sound, that's why I got green and red. If my sound was traveling with those muscle striations, it's not going to undergo as much attenuation as sound going against the grain. I compare this to when I get a haircut and the barber, cuts my hair against the grain. I don't like that. I'm like, bro, what you doing? Don't cut my hair against the grain. You gonna mess up everything I got going on. My waves, everything. So you got to cut with the grain, for it to be smooth, for it to have less attenuation. Okay, you have to go with the muscle fibers. All right. You go perpendicular to the muscle fibers, then it's gonna attenuate twice as much. Golden? Sweet, man, y'all ready to go. That's just what we talked about right there, guys. Table 6-4. Any questions on this? Any question on attenuation of media other than soft tissue? Any question on why air, why water?
Why we have to know the attenuation?
Why you have to know it? Because that's important to know how.
Frequency?
No, it's important to know how much sound is being lost over time as it's traveling in the body. Which, because if you didn't know that, then think about your TGC. Your TGC, you would just have a dark liver in the far field and a bright liver. If we didn't know that, we have to adjust that to make it even. It wouldn't be no point in doing ultrasound. It wouldn't be diagnostic. So you have to know the amount of attenuation and the degree of amplification, right? Because that's the whole purpose of the interaction of sound and media.
Bone and lung are even higher. What the meaning of even higher? They're the same. The same.
They have a high attenuation rate. They have they're comparing these from water all the way to air.
Okay.
So I'm saying it's going from low attenuation to high attenuation. You're right. I don't like the usage of those
low
words.
attenuation? Like it.
Sound is going to travel a lot easier. It's not going to weaken as less. Remember, attenuation means the weakening of sound as it's traveling. So if it has a low attenuation, that means it's not losing as much energy. Remember, in water, it almost doesn't lose. It doesn't lose any energy at a sound that's less than 10 megahertz. Okay, so that's what this is. Again, and the reason lung and air is because we need that. Thinking about it like this: a lot of these other structures right here, they contain some kind of fluid, right? The more fluid in the structure, the less attenuation. Okay, the more fluid. Think about water, blood, urine, all those have fluid in them. Fat has a lot more fluid in it than soft tissue, right? Because fat is real gelatinous, right? It's real jiggly, right? And then you have soft tissue is a little more stiffer. But if you know about the water, the body is made of 80% water, correct? Okay. So as we get muscle has less fluid in it than soft tissue, bone and lung don't have, that's air, right? So there's no fluid associated with that. So sound is gonna travel better in a fluid filled structure than it will in a solid structure. Okay. Remember, that's different. We're not talking about propagation speed. Because we know that sound travels faster in solids than it does in liquids. Okay? So those are different. Those are different. That's talking about propagation
Energy,
speed.
right?
We're talking about attenuation right here. The loss of energy. That's propagation speed is talking about the speed at which it's traveling through a medium.
Yeah, makes sense.
10 minutes. Am I over time? No, I got time.